Thank you for the introduction. So in fact, it's a conference about applications of AI. And I will do something a bit strange. I will give you a big warning about too much strong expectations that you may have about these applications in the near future in airplanes. In fact, Gary resumed perfectly what I will say. I will say in a different way. I will skip the motivation. It's obvious. It was the ATOL system of Airbus. So what is, and I will speak about a small part of robustness. It's not all robustness. It's a small part, but it's the most impressive one. It's adversarial attacks. So what is an adversarial attack? Here you have a student, probably in a Chinese university. I don't remember where I stole these pictures. And here he is correctly identified by the neural network. He is classified as a person. And now he discovers a strange drawing that he has on his chest. And it disappears. In fact, he has escaped detection because of this strange drawing on his chest. Okay? You can do the same thing with a sheet of paper with this drawing imprinted. And you will see that the escape will follow the sheet of paper. So the one who has the sheet of paper in front of him is invisible. And that's what occurs just now, because just now, with all these cameras and all the networks that are behind, all of you are identified by Big Brother. He knows that you are now in this room. All of you, but not me, because I am invisible. Okay? You have other applications of adversarial attacks. Okay? For example, here you can change a stop sign into a speed limitation, which may have bad effects. So I have to go quick because my slides are too important. Just to say that the critical year for us, the critical reference is 2020, where for the first time, DeepNets showed a performance much better than classical image processing. So 2 times better, in fact, than classical image processing. But only 2 years after, the dark side began to appear. So 2 years after, people of Google published a strange paper in which they showed how to perturbate images slightly, imperceptibly, but in order to completely change the classification. So in the middle columns, you have noise. In fact, this is amplified noise in order to see it. If you add 100 of this noise to the picture on the left, you obtain the picture on the right. And this picture is no more correctly identified by the network. In fact, in all the right columns, all the pictures, the 6 pictures, are identified as an ostrich. Okay? Next year, still stronger, they take a panda and they transform it in a monkey, a gibbon. But look at the confidence. The network is completely confident, more than 99%, that it's a monkey. Okay, he has completely been fooled in terms of classification. So those are adversarial attacks with noise, diffuse noise. Next year, for the first time, you have 2 differences. This is no more diffuse noise. This is concentrated noise attack. And this is also a physical attack. It's not on the image. It's in the physical world. So the glasses are physical. They are real glasses with a certain pattern, like this T-shirt. And so this guy is transformed into an actress. Okay? This year also is also important because it is the beginning of studies about this, serious studies about this subject. So DARPA launched his explainable AI project, which is a kind of ancestor of the Confiance AI project. Next year, you have the stop signs that we have seen also this morning, I think. Okay. Next year, it made the buzz, but in fact, it's half a lie. Those are 1 pixel attack. You change 1 pixel. The trick is that these images are very small. there are only 32 by 32 pictures. And so 1 pixel contains a significant energy compared to the whole picture. So that's why you can do an attack with 1 pixel. On real VGA images, it's impossible. You cannot fool a detector with only 1 pixel in a real image. But it made the buzz. The t-shirt also. So first on a sheet of paper. What is interesting is that they remarked that they tried, but they failed to transfer the attack. So they designed the attack against yellow, but they failed to transfer the attack onto another network. And so the attack was specific to a particular network, a particular white box. But soon after, another team, and my t-shirts comes from this paper. First of all, they did a physical attack with, and what is interesting with the t-shirt is that it's curvy, okay, and the curvature depends on people also, and it's moving, okay, and you see that here in the middle, the hidden guy reappears, because in fact, it's not so easy with a moving target to all times escape the detection. So moving, curvy, much more difficult. Okay. So I bought mine on Amazon, but if you want something more stylish, you can go on this YouTube page and you will see more sophisticated clothes. Same year also, military attacks. So people are taking military vessels and they are fooling detectors which classify them into civilian or military. So all these military vessels are completely, with confidence, classified as civilian. Okay. And next year, the same thing. No, it's a pure escape, this one. So for ground targets seen by satellites. So instead of putting a physical net, you put an adversarial patch, and you see that you can make disappear anything that is interesting in the ground, on the ground. Okay, so it was the teasing part for motivating the message. The message is that things very strange occur in deep networks, and we are just beginning to understand what's happening. And so I will to share this fact with you in order for you to understand that the road to a critical deep networks into a plane will be long, very long. So what is underfitting and overfitting? It's a classical subject in statistics. So you want to fit a curve. So basically, it's a quadratic curve. It's a degree 2 polynomial with noise. And so you want to fit, you want to guess what is behind the noise. So on the left, I try to fit with a straight line. On the right, with a complex polynomial. And in the middle, with quadratic polynomial also. Of course, it is the middle which is the best fit. On the left, we see that we have systematic errors because a straight line is not a curve. So whatever the straight line you put, you will always have errors. So this is what we call underfitting. And on the right, you see that you have a perfect fit. But this is bad. This is called overfitting because, in fact, your model, your high degree polynomial, was so powerful that it has learned noise. There was no filtering of noise. It has learned noise. And so if you change the sampling of the points, if you change the crosses on the same curves of the second degree, this estimate, this transfer will give bad results. Because your new crosses will not be on the old ones, they will be in the middle of the old ones. And you see that in the middle, the estimation is just nonsense. Okay? So we say that you don't generalize. You overfit, you have learned noise, and learning noise is a bad thing, and it leads to no generalization. Okay? It's a general phenomenon. The problem is what? The problem, in fact, is the slope. We have too important slopes into the new model, into the complex model on the right. Because this slope enable low power disturbance. You put a small shift into the x-axis, and you have an important shift in the y-axis. And so you have an error of classification, of estimation. And so this is what happened with our adversarial attacks. Low power attacks can create big effects, can create change of classification. And so the solution, the classical solution of statisticians or the new solution of machine learning is to limit the slopes. But in machine learning, the slope is not called the slope. It will be too simple. It is called the Lipschitz constant. Lipschitz constant. You have to memorize this term. Okay? It just means it is the slope, the worst slope in the model. Just that, the derivative. Okay, but you look more clever if you say that it is a Lipschitz constant. And so we apply all the cooking recipes. Here it is an example of what is called ridge regression. When you do linear regressions with hydroid polynomials on the left, you got completely nonsensical estimators. They don't generalize, the same problem than before. And the solution is to limit the weights, to calm the weights. So statisticians are used to say, I want to limit the weights. Look at the weights on the left. They are enormous. The values are not important. The y-axis is, you see 25, 30, small values, but the weights of the polynomial are huge. If you count the weights, you get a better estimator. But on the right, if you calm too much the weights, you again get a bad estimator, but not for the same reason, not because you are overfitting, but because you are underfitting. Okay? So choosing the good solution is not always obvious, but it's what we do. And so this was seen from the beginning by the first guys who saw the problem, who transformed the Dufour school into an ostrich. Okay, and they suggested this, and today it is the main line of defense against adversarial attacks. Okay, this line of defense is limiting the Lipschitz constants, limiting the derivative inside the network. And so since 10 years, you see a lot of papers with how to limit how to train the network in such a way that it gives naturally small Lipschitz constants. And people have begun to say, oh, yeah, I bring guarantees and I bring certificates. I have a certified defense. Okay. So when I saw that for the first time, I saw, oh, what are these certificates? And in fact, when you look at these certificates, they are mathematical complex objects. Okay. And the problem is that they have no direct link, they have no obvious link with safety objectives. Okay. You have no obvious link with hazardous events. And even with failure mode, with potential failure mode. So you have no link with the world of safety. I will take an example. Since 10 minutes, maybe more, I am speaking to you about adversarial attacks. But I have not defined rigorously what is an adversarial attack. Why? Because I don't know how to define it. In fact, nobody knows how to define an adversarial attack. Okay, so we are speaking about things that we cannot define. So you begin to see the size of the problem. And in fact, you cannot just say it's a low power attack. We can maybe develop this later, but it's not enough to characterize an adversarial attack. So this is the first problem on the roadmap to critical AI, Okay. The second problem, in fact, the second problem incorporates the first. It's bigger, it's in the bigger scope. It's on the generalization theory itself. It's the theory which says, why is it bad to underfit? Why is it bad to overfit? And how do you avoid to underfit and to overfit? And as Gary said, how do you ensure that the errors that you saw during the design of the network are a good indication of the errors that you will have in real life? This is the main point. Okay? For certification for safety, you have to anticipate the errors in real life. And for this, the main tool is the errors during design of the network. What is the link between both? This is the subject of generalization theory. So generalization theory is a big theory. I have no time. I have no 3 minutes. So I have no time. Just, I want to show you that. I take a complex model and I train it, so I obtain, so you have a perfect fit on all the crosses. It goes through exactly through all the crosses, but between the crosses, it is just nonsensical. If you change the sampling set, the training set, it changes, okay? It completely changes. Estimators are unstable. And when you draw them, when you do a full sampling, you saw that you have a full cloud, and this cloud is called the variance. And this variance explains why, in fact, this is an indication of the test error. When you will show to the network new tests that he has not seen before, this is the error that you will have. So, sorry, I have no time, but usually, 10 years ago, the classical dogma of statistics was, on abscissa, it's not the training time, it's the complexity of the model. On the left, you take the right drawing. On the left, you have simple models, and as you go more to the right, you have more complex models. And what this curve says is that at the beginning, you have the curve on the top, the U curve is the error curve on the test set. Okay, this test set has not been used during training. It's an independent test set, which is reserved for assessing in the end. And so the error on the test set on simple models will be high because underfitting, will be low because of on the right it is right, it is important also because of overfitting, the other reason, and in the middle you have an optimum. So this U curve is a dogma of classical statistics since 100 years. Okay, and what we have learned since 10 years is that this dogma is wrong. Because in fact, if you overfit on deep networks, okay, sometimes this dogma is true, sometimes the dogma is false. But if you overfit on deep networks, or here it is not deep networks, it is AdaBoost, it's another learning method. In fact, it can the test error can continue to decrease. And so this is in 1998. This is the first time that this phenomenon was documented in a paper. Okay. In a minute. So it was not noticed at the time. So we have to jump into 15 years later. So it has been documented here. So you see here that the test error decreases. You have a beginning of U. This is the blue curve. You have the beginning of a U, but after that, it continues to decrease. And so with such an important phenomenon, you have to give it a name. And so in the name for this, you will hear of this, I think, it's double descent. It's not a U curve. You have a U, and then after the U, you descend. You have a double descent. You have a first descent, and you have, if you continue to overfit, to complexify the model, it will continue to descend. So it is documented here in this paper. You see the double descent here. If I have the laser. First descent, second descent. Okay. What is important is that it's not the double descent per se. Is that if you continue, you you are better than in the U. That is, you have better performance if you continue to overfit. That is, the first minimum is a local minimum. It's not the absolute performance. What it means is that for deep models, it is mandatory to overfit. If you use a deep model without overfitting, it's not intelligent. It's not the good way to use a deep model. Okay. So conclusion. No. In fact, you have no double descent. People have seen that you have triple descent. After that, you have seen that you have quadruple descent. And in the end, people have seen you have as many descents as you want. Okay, it does that. Okay. So to sum up, we have I have illustrated two problems. The first problem is that we have a cultural problem. We have a missing link between people who are doing theory, mathematics, learning theory, and safety engineers. There are no links today, clear links with safety. And so my first hint would be you have to reinforce collaboration, industry, and academy. Okay, and typically conference programs are the good place to do that. And you have to integrate safety engineers. Today, they are not in the loop, and you have to put them in the loop. Second thing, you have a fundamental problem about generalization theory. And so in industry, the only thing that you have to do is to integrate statisticians. And I have written statisticians. It's not data scientists. It's a statistician. Okay? It's not the guy who applies the cooking recipes. It's the guy who understands them and who is able to adapt them. Okay. Thank you.
Thank you.